Hi, welcome to this third video in this video tutorial series. So far, we have seen how we can set up a Python environment fairly easily for federated learning simulations using Flower. In the second video, we saw how you can take an off-the-shelf dataset, in this case MNIST, and partition it into 100 clients. So every client in the federated learning experiment gets its own dataset for training and for validation. In this video, we're going to see how you can set up your Flower clients and highlight what are the key methods these type of objects have. We're going to use this video also to present the model we're going to use to train in a federated fashion, which is going to be a CNN for image classification. So without further ado, let's get into the video.
So let's continue our tutorial by doing exactly that. This is where we left our workspace. What we need to do now is to do something here that will enable our virtual client engine to spawn clients in every run. So for that, let's start by creating a new Python script that we are going to call client.py. So let's define a class called Flower client, and this class is going to inherit from a built-in class in Flower called NumPy client. Let's start by defining our init method, and some of the arguments we might want to pass to this client is things related to what is the dataset this client should be using. And we know from what we did before that our dataset preparation script, what it returns us is a list of data loaders. Each data loader corresponds to one client. So when we create this client object, what we are going to be passing is one train loader, the one corresponding to this particular client, and the same for the validation loader. And because the client needs to know a little bit more about the dataset, for example, to instantiate correctly the model, we might want to pass additional arguments like, for example, the number of classes in our dataset. We could retrieve this information from the data loaders, but doing it like this is a bit cleaner in my opinion. So let's first make sure that these variables persist after initialization. So loader, self loader, and then what we're going to do, let me just call classes. What we're going to do is also instantiate the model that this client is going to be training. So to do that, we are going to do self.model equals let's say a network that is going to be of type net, that we haven't defined it yet, but we will define once we finish with the client. And this class will expect an input argument telling it what's the number of classes to, for example, adjust the output fully connected layer accordingly. So that looks good. Another thing that we want to set in the client is what resources this client should use, and in particular, what device should the training and evaluation be used. And this means, do we want the client to train using the CPU, or do we want the client to train using the GPU? We could hard code it here if we know this in advance, but in some cases we might want to change this not from the client, but from the place where we start our simulation. So because that's a desired place, what will happen here is that the client will set as device the device that is available at any particular time. So what we are going to do is to first import torch, and then torch device is going to be the GPU if torch CUDA is available, else we're going to use the CPU. And then whether we launch the simulation with the GPU support or without, the client will use the device that is specified from the point where we launch the simulation. Alright, so that's how we are gonna create our clients. Each client is gonna have a train loader, its own validation loader, it's gonna have a model that at the beginning, at this particular point, this model is uninitialized, so it's going to be, well, it is initialized, but it just has random weights. What will happen is that when this client is told to participate in a round, it will receive the model parameters from the server, and the weights in this model will be overwritten by those sent by the server. And where do we do that? We do that in a method that is called fit. The fit method is probably the most important method in a client in Flower, which, as I mentioned, will receive one main argument, which is called parameters. This argument is a list of NumPy arrays representing the current state of the global model. And there is a second argument that is, you can think of it as a Python dictionary, like a config file, that tells the client, oh, look, at this is additional information relevant for you to consider in this particular round of training. So at the beginning of the fit, we get the parameters from the server and a configuration sent by the server. What we need to do now is to copy the parameters sent by the server into client's local model. So we are going to do that, and we are going to do that by defining another method that is part of the NumPy client class that is called set parameters, which is going to receive as input argument the parameters that we get from the server, and that's it. And what's going to happen here? Remember, we decided to use PyTorch in this for this tutorial. So parameters is a list of NumPy arrays, and we have a model. What we need to do is to set the state ticked of this model with the parameters provided by the server. So let's just do that. Let's create first let's start creating the dictionary that will become our static eventually. So if we get the model and we get our state ticked, we get the names of every element in the state ticked, and because parameters is in order, that's something that has to be done properly from the server. We are certain that the state ticked can be constructed like this. So first I need to import order ticked. And then what we're going to do is that for every key and value in params_d, we are going to construct it. We're going to construct a dictionary just like this. So we are converting every element in my NumPy array into a PyTorch tensor representation. And now with this, we can just make this the new state ticked of my model that is already, it has already been instantiated here. Not set, load. And let's make sure it is strict. All right, so now we can just call this method. So now we have the model in the client now has the weights and other parameters sent by the server. So the next step is to actually train this model locally. And how do we do that? First, what we would want to do is to look at the config and extract any configuration parameter, any hyperparameter relevant for training. In this case, if we go back here, I talked very briefly about it earlier, but this essentially will be sent by my strategy, which is the algorithm that lives in the server and orchestrates the entire federated learning process. The strategy will eventually send these parameters at the beginning of every round and for every model, every client. So the strategy will be sending to this particular client, these are the parameters and these are the configurations. So let's extract, for example, the learning rate, and let's extract also the momentum. And one thing that is important is, for example, we can use these arguments to define our optimizer. We can use, for example, good old SED, and for that we pass the parameters of a model. I set the learning rate to use learning rate and momentum. All right, and now what I would need to do is to call the training function, right? Do local training. And you can think of, you can decide, okay, now let's define a training function, and this training function is really not going to look any different from your typical training function that you might have written already many times in PyTorch. So let's jump quickly into that so we can define this instead of doing that later. So for that, in order to define our training function as well as our model, we're going to jump into, first we're going to save, and then we're going to create a new file called model.py. And in this file, I'm not going to create anything as super fancy. I'm going to just use one of my existing models from other projects. So I'm going to just copy paste it because this part doesn't have anything special about Flower or any Flower dependencies whatsoever. So you can see here, I'm defining a very standard, very basic CNN comprised of just two convolutional layers and 3 fully connected layers. Pay attention because we are using MNIST. MNIST is a grayscale dataset, so the input channels is 1. And you can see that I'm expanding to only 6 channels and then to 16. And the hidden dimension of this stack of linear layers is the maximum you will see is 120. So this is fairly small, but good enough for our dataset, which is MNIST. And then another 2 helper functions I'm going to borrow from very typical PyTorch projects are these 2 functions, which is just a standard training function. So it will take the model, a train loader, an optimizer, number of epochs that we want to do this training, and the device. So this would be either CPU or GPU. And as you can see, if you are already familiar with PyTorch, there is nothing new here. This is a very standard training loop. And similarly, here with test, the purpose of this would be to pass the model and evaluate its state in a held out validation set or in the test set. And in this case, we are particularly interested in getting what's the loss and what's the accuracy of this model. So now that we have defined this model, training function and standard test function, we can go back to our client and then let's import that from model import net. We're going to import train, and we're going to import test as well. So now this was detected properly. And now let's continue where we left it. So here we're going to call our train function, which, as we just saw a few seconds ago, it requires very standard input arguments. So it requires our model that currently is using the state of the global model in the server that has been sent. We're going to use the train loader of this client. We're going to use the optimizer we just defined. Number of epochs, actually number of epochs we will do is also something we want the server to tell the client, for instance. So epochs. And this, I think it's good practice to call these local epochs, because this refers to how many epochs a client is going to train locally. And by locally, it means that the global model is going to be trained on the data that is local to a client. So we want to set that here as well. And finally, we need to pass the device. And before we forget, let's copy these local epochs and pass it here. And as a standard, I'm going to use only one local epoch. All right, so this is how the fit method looks like. At this point, we have completed training, so the model no longer has the exact same weights as those sent by the server. What we need to do now is, before this client ends its local training stage, we want to send back the updated model back to the server. So the way to return from this fit method is as follows. So we need first to extract the parameters from the PyTorch model we have, and we are going to do that in another method that we need to define, that is called getParameters. In addition, we're going to return a bit of information of how this data set is, some statistics about this dataset. In particular, we're just going to send how many training examples this client used. So you can do this by doing len self train loader. And why are we sending this information, you might ask? We're going to be using an aggregation method called Federated, and a version of it requires knowing how many training examples were used by every client. In some situations, you might not want to share this information or any information at all. If you are super strict, or if you are required to be super strict about privacy. But one of the benefits of simulation is that you can see, for instance, very easily what's the impact of my training procedure if my server has access to this information or if it doesn't. And you can experiment with different degrees of privacy, for instance. But that's a topic for another video. Let's continue with the return statement. The final return argument is something that we call metrics. So a metrics is a dictionary where you can add pretty much anything you want to send back to the server. So as I said earlier, maybe you want to send additional information. For example, you want to tell how long it took to the client to train, or you want to send information of how much energy, how much battery this client used to train the model. Different bits of information might be okay depending on your privacy budget. The benefits of simulation is that you can play around with these return arguments to better adjust your algorithm, or to have a good overview of every variable involved in your training process. So you could send other statistics here. But before we finish, we need to set this final method that is called getParameters, which is, okay, finally the auto-completion worked. And what we're going to do, let me remove this. What this method should do is basically revert this process. Earlier, we had a list of NumPy arrays. That is what the server sent us. And we copy those into the model. Now we need to do the opposite. Let's extract a list of number arrays from our model. So we can do that fairly easily in just a single line. So we'll do for every, let's say, key and value in the static of my model, self model, what we're gonna do is we're gonna first ensure that my tensor is in the CPU, and then we're gonna convert it to NumPy. So this, I think, looks correct for me. It's going to be doing exactly that. Extract every element of the static of my model, move it to CPU in case it's not there already, and then convert it to NumPy and return. So this is pretty much how a Flower client looks like. There is a final method that you might want to implement as well, which is, instead of fit, is call evaluate. Which what it does is, let me just keep this a bit cleaner. What it does is it receives the global model from the server, and the idea here would be that we don't want to modify the global model. We just want to evaluate how the global model performs on the validation set of this particular client. This is a common way of evaluating the global model if, for instance, there is not a global validation set or a global test set. In many cases, you don't have one. So the only way to assess the performance of the model is to sample a few clients and see how the global model is converging into a good state. So we need to first start by copying the parameters into the local model. And then what we're going to be doing is to just call the test function we defined earlier in our model.py. We're going to be passing the model. We're going to be passing the validation loader of this client, and we're going to be passing as well the device. And in this function, if you remember, what we are returning is the loss and the accuracy, which is something we care about, and something we are going to report back to the server in order to have a sense of how the global model is doing. And we're going to return it like this. So let's ensure that the loss is a float. The next argument that we need to send is similar to the one we did above. Here we want to tell the server how many examples were in the validation loader. This information is useful, for example, if you want to aggregate all these individual losses or accuracies every client is going to use, and you want to if you want to derive a single scalar out of many of these metrics, you want to do the average based on how many images every client had, for instance. And here now we're going to make use of this additional argument called metrics to send the accuracy value that we obtain. And with this, we are done defining the client class. So just as a short recap, the client class in Flower has two main methods. One is called fit and the one is evaluate. Fit receives the current global model and trains it using the local dataset, and then it sends it back to the server where it will be aggregated. The other method is called evaluate. It has a very similar signature, as you can see, but here the key difference is that we are not modifying the model. We are just evaluating the state of the global model on the local data distribution of the client. Usually you will do this in the distribution held out for validation. In order to run both fit and evaluate, we need two auxiliary methods. One is set parameters that copies the parameters sent to the server into your model representation, because remember, parameters is a list of NumPy arrays. So probably your model is going to be in TensorFlow or PyTorch or JAX. So here is where you will be copying those parameters into your model. And then get parameters does just the opposite. It extracts the model from your it extracts the weight from your parameter it extracts the weights from your model and represents them in a list of NumPy arrays, which can be understood by the server. All right, but now the way simulation works is a bit peculiar, and what we need is to, when we launch a simulation, we don't want to pass it a client class. What we need to pass it instead is a function that can be called by the server in order to spawn a client. And why we do it like this is because we are simulating these clients. So at the beginning of every round, the server will know, oh, I have 100 clients with client ID from 0 to 100, from 0 to 99. What I'm going to do now is I'm going to spawn 10 of them at random. So in order to perform this spawning, what we need to provide to the server is a function. So let's do it just like that. So we're going to call, but we want to parameterize this function from a convenient place, like the main script. So let's define a function like generate client function. And this client function is going to be called by the main. We're going to call it right from here. And well, let's talk about the input arguments later. But inside this function is going to return me a client function. And this client function needs to have a single argument, which is the client ID. And what this function is going to do is going to return a Flower client. So let me just recap. Of course, we are not done with the arguments, but let's recap now. I'm going to be calling this function from the main. Actually, we can put it here already. This function is going to be passed to my server. So the server, at any point in the federated learning process, can execute it, saying, oh, I want to spawn client with client ID 4. I want to spawn client with client ID 99, for instance. So the only way to achieve this is by the server to call this function. And how do we make everything work? So what we need to do is to pass to this function the train loaders, loaders, and the additional argument we need for our clients, which is num classes. And what we are going to do is this. The Flower client, if you remember, needs to receive the train loader for this particular client. So the train loader for this particular client is like this. Can be obtained like that. So if this is the 11th client, then we are going to extract the 11th element in our list of train loaders. And we follow a similar logic for the validation loaders. And num classes, well, is the same for all of them. So this looks good. So this is what the main is going to call, and let's set it already from here. So from client import, and in this function, what we're gonna be doing, what we need to pass is train loaders, validation loaders, and also the number of classes which comes from the config file. So we're gonna say config.num classes, which we haven't defined, so we need to define 10 because we are using mnist that has 10 classes. Alright, so let's remove this because we already completed it. Okay, so now we have completed everything regarding the client. So we show how to define a very standard but complete client using Flower. It has two main methods, the feed and evaluate, and two auxiliary methods, set parameters and get parameters. And the way to create these clients, to spawn these clients or wake up these clients for simulation is through a function that is going to be called by the strategy in the server. And this function is going to pass a single argument, which is the client ID of the client that is supposed to participate in a given round. The strategy will use that client ID to access the specific train loader and validation loader assigned to this particular client. And this is how we define our clients and how we get a function that can be passed to the strategy, which is what we are going to be doing next.